Okay, guys, welcome back. Happy Chinese New Year, by the way. The plan to have a class in person Wednesday, unless Mother Nature has another thing to do, okay? There's a huge storm, snow, whatever, I don't care. As long as I can drive my car, hopefully I will be in my office and I will give a class in person Wednesday. That's the plan. But who knows? Anyway, so one quick, I think I received email about the repository. As you know that we do have a two TAs, okay? If you go all back to the shared Google document that we share with you in order to allow you to choose or form the groups for the coding assignments, you're gonna see that I add another column, okay, in the so for each single group, you need to double check who's your TA responsible for grading your coding assignment. So simplify the process to see who you wanted to communicate with, yeah, and also I believe the TAs already submit or send you emails about their office hours. Even if these office hours doesn't work with you guys, you can reach out the TA and CC me at the same time in that email, asking for another time if you have any question about the coding assignments. I expect the TA is gonna submit or send maybe by the end of today. That's what they promised me. The repository. They're gonna create a repository, then I'm gonna share it with you hopefully by the end of the today. You need to have access to that for your server, okay? The problem here, it's out of our control. It's not me, it's not the TA is going to generate to create this, the accounts at that server, okay? So I expect from them, I already sent a request with your names, so I believe maybe today, maybe tomorrow, I cannot control when they're gonna apply. Once they're gonna apply, they're gonna send you email with your credential, with the access. How can you use, what's the username and password, and how can we access your account? Yeah, so hopefully that answered the question. William, I believe, William sent that question, I believe, this email. Anyway, let me remind you what we did last time. We talked about the page layout, the file layout, and etc. Okay, in general, we talk about the structure of the page in general. Okay, we went over. Let me check first, make sure that in the right place. Yeah. So remember that we have two problems we need to study, right? The first one, how the database management system going to handle large amount of data. In other words, how the database management system is going to store or represent this data on disk. In other words, how the database management system lay out the data on disk. We're still in this first problem. Hopefully we're going to finish this one today, and the next lecture we're going to take a look at the second problem or second issue, which defined as how the database management system manages its memory, yeah, and move the data back and forth from the disk to the main memory. In other words, we're going to talk about the buffer pool. Last time we discussed how can we organize the database across sequence of pages, right? That's what we did here. We said that we have a file, and this is the file that you want to store the data that we have. Okay, the file might be a relation, and this relation might be, for example, the ID, name, or whatever. This data can be stored. That's my data. I want to store this one in the disk. First, we're going to set the file or data can be organized as a sequence of what? Of pages. So it might be have a page 1, page 2, whatever number of pages. We can store this one, the page on the disk. We want over the page layout, and we know the structure of each page looks like something like this, right? We have a header and a slot page or slot array, which allow me in order to navigate my way within this page, right? Then after that, we talk about the way how the data can be stored within the page itself as a record. Yeah? As a sequence of bytes, records, and the record is going to be with the tuple has a special structure. It's going to be has a header, and here we're going to have what? The data that going to be stored here. Then in this chapter, we talk about the data storage part 2 here. We want over the how can we lay out store the actual data on the disk, right? We take a look to, for example, how the database management system is going to represent the individual attributes. For example, if we have a string, if we have a char, if you have integer, if you have date, time, whatever, how the database management system can store this one in the list. We did this part. And we said that the database management system is going to have what, like a schema, like let's say catalog. Based on this data or this catalog, the database management system can understand what's going on in the disk, what's going on in the data. The operating system doesn't know anything about this one. The only thing that operating system knows about the system, a sequence of bytes. If you want for me to retrieve it to you, I would be happy to do that. Okay? Not exactly, but we assume that the operating system can talk to us like this. So anyway, so to summarize that, so it looks like the data can be stored like, I need just to have a space here. Let me have the whiteboard here. Yeah. So now we know exactly the data can be stored in that file, yeah, as blocks. This is the coding assignment, let's say programming assignment 1. Not the actual one, we're gonna have a simple way to do that. And remember, when I said the data can be organized as a sequence of pages or blocks, it's gonna be stored on the disk, we need to figure out how can we find out where my data can be stored. Yeah, for example, the high level, the query maybe engine said, okay, I want page 5 or 6. So the database management system take care of this one and fetch that page to the main memory if the page does not exist. How the database management system knows where the data can be organized or stored? Using the, they'll show you the heap structure, yeah, file organization, with the simple way to do that. In the heap file, we said the data can be organized in any place. I don't care about the order, but I'm still being able, I need to care about how can I navigate my way. That's why we create special pages. We call this one page directories, where they're gonna tell me navigate my way, how find out the data exists or not, the pages exist or not, which one is gonna where the data is gonna be actually stored in the disk, how can we reach them, and also which one has enough space, right? Then after that, the second step here, we saw the actual data can be stored here, how the data can be stored here. So we have a sequence of, let's say, bytes, but we have an organized way, right? Because we have a header, and they can tell, for example, what the content of the file. Sorry, the tuple. Then in the next level here, we have something here, and we, by the way, we looked into the actual how the page looks like. Then after that, we have a second level here, the buffer pool, which is going to be the second coding assignment. Here I need to do what? I need to fetch the data back and forth as the pages or blocks from the disk to the main memory. And I need to store whatever. Sometimes you need to reflect the change from the disk of main memory to the disk. Especially when you fetch the page in the main memory, modify this page, then after that, you need to store this one back. This is the second coding assignment. Of course, in the buffer pool, we're going to see we have some organization. We need to figure out the way, how can we search within the buffer pool? We're going to take a look at this one later. Okay? Another thing here, we'll start looking at the different way how to organize the data on the disk. And remember when you talk about the sequential, but try to put the data in sequential or sequential access the data, it's gonna be help us, or to say, mitigate the effect or speed up the access to the data, right? If you have a sequential access to the data compared to the random access, right? That's one thing. The second one, I believe, we are going to start looking at today here. Do we need to store the entire tuple, the attributes that belong to the same tuple together, or maybe break it down? In other words, right now we assume that we have the data here, yeah? And for example, the file is going to be ID, name, and GBA, and whatever. And for every single tuple, we assume this tuple can be stored as one unit together, right? In the same page. But someone is going to say, okay, maybe this is not the good idea. Maybe this is not working. It depends on the workload. You're familiar with the workload, right? We say that workload here, we have different types of workloads with the type of the, let's say, the activity, the query that I'm going to perform in the database. For example, I mainly perform reading operations. My query that I'm going to perform mainly reading operation, I'm going to read a large amount of data, then I'm going to derive some information. That's one kind of workload. Another kind of workload I'm going to perform mainly I just modify or perform writing operation. And usually I touch small amount of data. Another kind of query or task require maybe I don't need to have access to the entire relations or table that we have. I need only specific attributes that mainly that I'm interested in. For example, I'm just looking for the grade in order to compute, for example, the who's one get some insight or derive some information, for example, who's the highest grade in this class, or based on the GPA, you need to find who's the student with the highest GPA, and etc. Okay? So that's the one that we're going to try to look at right now here. Then after that, we're going to see how can we perform some operation, insertion, deletion, updating a tuple within a page. Okay? Let's go back to the slides first, then see how can we go back here. Let me check here. Yeah. So we're going to take a look at different ways. How can you store the tuple in the page itself? Whether it's going to be in the entire tuple together or break it down. Before that, you are familiar with the relational model, right? When you talk about the relational model, it's defined as what? The way that how can you organize the data in the logical. Logical phase, yeah? So the data model is what? The logical structure of the database in general, which just help me describe, the design of the database. To reflect, for example, talk about the entities, attributes, relations among the data, and etc., right? And constraint, and etc., right? So we talk about the relational data model. With the one, of course, it's going to be one of the form, the data model. But in the relational model, we said that the data is going to be stored as what? As a tables, right? The entity will have a table, have a list of table, and each table is going to have columns and rows. The columns are going to represent, the attributes, and the rows are going to represent, the corresponding value for, let's say, every single entity within this entity set. All right? In the relational data model, they didn't say that you have to store your data together. All the tuples or attributes, all the attributes that belong to one tuple or one relation must be stored together. No, they didn't say anything. So that's a good thing. So the way that you store your data, for example, if you store all the attributes that belong to the tuple together, this one is not work based on the workload that we have. And again, when we talk about the workload, I define this one as a what here, as I mentioned here. It looks like you have what? It depends on what? What the nature of the request, okay, or the task a system will have to handle. My database, as you mentioned, depends on what kind of a query. Heavy, let's say, reading, writing, touch large amount of data, read the entire data of the system in order to derive new information, or maybe update just student name or touch maybe small amount of data and mainly going to be updating or adding new information. Based on the workload, maybe the way that I'm laying out the data is not good. Okay? So let's give you an example here. Assume that we're going to talk about the Wikipedia in general. This is a simple example here. So in the Wikipedia here, we assume that we have 3 tables, okay? The first table is the user count. The second one is going to be the pages. And the third one is going to be the revision. So take a look at the revisions here. In the Wikipedia, we do have many pages, yeah? For every single page, maybe have a multiple or many versions, okay? The first one, then someone update this one, going to produce a new one, and etc. Sorry. Yeah? So here we have like many revisions. These revisions for the same page can be written or be created, modified by whom? By the user. So as a user, you must have an account. Once you have an account, you can add a new revision or create a new page. If this page has only one revision or one version, then you are the only one who create this one. If you modify this one again or someone else modify this page, now we have a more different revision of this page. The page table is going to keep tracking for what? For the most recent or the latest version of for a particular page. Makes sense, the structure? So I have a users, create pages. For every single page, maybe have a multiple versions. And here we need just to keep tracking to the most recent one. Of course, you see that we have a say foreign key constraint here to make sure that the page and have a user that creates this page or creates the revision must be exist. And also, when you have a page has a specific revision, this specific revision or version must exist. That's the structure here. So just to give you sample data, and now we have go over a few queries. Yeah, and we'll try using this query, try to introduce you or to say go over different workloads here. Okay, the first one or the first workload that we know here was the online transaction processing. What does that mean in this case? In the online transaction processing here, this is one kind of workload. Remember, we talk about the workload to say that the nature of the requests a system will handle. Yeah, what kind of query is going to perform here? Usually, what kind of query? What kind of task your data is going to perform? So it depends what kind of tasks, yeah? You send some queries, what's the nature of these queries, okay? So the online transaction processing here, it's going to have, it's got categorized, this workload categorized by what? By fast, short, running operation. So you have a query, fast, short. It's not lengthy one. It's going to spend less time than the other workload, okay? You want to access your data. You want to check, for example, let's say you want to add a new revision. Yeah? You want to say update user account. You're going to the Amazon account and you're going to perform some purchase. You're looking for a specific item, then you purchase this item, you do the transaction, and done. Limited time, fast, short running operation. Simple queries. It's not complicated one. Yeah, I insert, delete, modify, and etc. Okay, and also operate on the single entity at a time. You insert, for example, modify your account, single entity. You insert a new revision, single entity. Here we're going to talk about this one. This kind of query. Okay, this is, for example, try to do what in this case. Yeah, try to achieve, the latest version for a particular given page, right? Yeah. So still. Simple query, all right? Good. This kind of query mainly or typically handle more writes than reads. So it looks like this one kind of the application of that the people built first. For example, look in an Amazon account, you create an account, you do some transaction and store some information. Yeah, that's the simple thing. The second kind of a query, the workload is called online analytical processing. So this one is, we try to compare this one with the online transaction processing here. This is different. This is characterized by what? By long running, it's not short. That one is fast, this one can be long running. For example, I need to have what? Yeah, I like this one, I think we have one examples here. Yeah, I tried to find this, say, the 5 most bought items over 1 month period for, let's say, Chicago area or Illinois state. I need to check what the top 5, let's say, bought items in Amazon during this period for the based on the geographic area, or in the United States. You see how many bunch of data you need to access. You're going to use a huge amount of data. All the transactions done or made by all the users during this time. You see that you're going to read a large amount of data. You're going to touch more than one entity. It's not single entity. You're going to perform many accounts, many users, perform many reading operation, very, they say, complex query. Then at the end, you're going to say, oh, those are you're going to derive new information, right? Okay, it looks like I'm talking about the CS425 introduction to the database organization. So anyway, we have 2 different workloads. Each of them have like different structure. Okay, one is fast, short. That one is simple. Okay, the other one is going to be long running, complex, read large amount of data in order to deduce or derive new data. So you're analyzing and deriving whatever data that you're looking for. You're analyzing what? You derive the data what? From the data that collected by the online transaction processing. You keep what? How can you collect the data? We have multiple users, do simple queries, simple operation, create accounts, buy new items, list items, and etc. Then after that, I'm gonna try to read all this information in order to produce the result that I'm looking for. Anyway, we'll give you a simple example here for this kind of query. So this query is going to perform what here? try to get what? Try to count, okay, the number of users that logged in our per month, okay, count the number of users per month that logged to this website from the hostname government. Okay, you can't change this one from the IIT.edu, the server, or the Comcast, or whatever. So when someone tries to log in the system here, I need to check what the host name that used, what the IP address that his user tried to log into the system. So in this case, I need to collect, I need to figure out to find out for per month, count how many users access the system, and I need to make sure that before the count, these users must log in or satisfy the condition that log in from the government website. Okay? So you see that we're going to read the large amount of data in order to deduce the final result. Okay. So it looks like we have mainly two workloads. Actually, we have a three workload. The third one is called hybrid transaction with analytical processing. It's going to be two in one. It's going to be have the online transaction and analytical processing at the same time in the same instance of the database. Okay, we are not going to work out that one. So mainly we're going to focus on OLAP or OLTP, I mean online transaction processing and online analytical processing, and see what if I store my data based all the attributes that belongs to one is going to be stored together. What if, see, we have kind of workload is OLTP or OLAP. Whether it's going to be fit, which one going to be fit better. Then after that, say maybe you have a different ways. Maybe what if I, let's say, split the data column based or column store, then you see based on the workload which one fit better. Okay? We don't have one way to lay out the data that can fit the OLAP and OLTP. It depends on workload. You need to find out, you need to store your data differently. Okay? Let me go over the simple thing here. This is a summary between both of them. Okay? Mainly one of reading, mainly writing. One spend long time, read a large amount of data, was other one reading small amount of data, touch one single entity, that one heavy, let's say, complex square. Anyway. So the simple data storage right now, when you store the data in the disk, we assume that we have what? The raw storage, with the simple way that to store your data. So what does that mean in this case? We are going to store the tuples, okay, as together in one, let's say, unit. So in this case, if we have, let's be here, assume that we have the relation here, and the relation R is going to have a specific number of tuples here, okay? I mean, relation R, and relation R has, let's say, number of tuples and columns, let's say 1, 2, 3, 4, which is going to be the number of columns that we have. For every single tuple, I'm going to do what? I'm going to store all the attributes for the single tuple continuously in a single page. So that means the information here is going to be stored on the same page. Okay? If we need another tuple here, the next one, all the tuples or the attributes for this tuple is going to be stored together as one unit. I'm not going to split them. That's one way here. Okay? In order to check, we see whether it's going to fit to work fine with if we have online transaction processing workload or if we have the online analytical processing. You see, for the online transaction processing, what you're doing here usually, you touch maybe one entity. For example, if you say select a star from the relation R, where the student ID equals specific value. So here in this case, I'm going to perform one discount out operation, right? If we assume that we have an index and they manage to find out which block that I'm looking for. When you fetch this block that contains the information, you're going to find all the attributes, the value of all the attributes that you're looking for, right? Because all the attributes get for this tuple is going to be stored next to each other continuously and the same page. Make sense? Good. Let's take a look example here. Again, I'm going to store the information that we have, the data that we talk about, the Wikipedia. And in this case here, all the attributes that belong to, for example, the user account can be stored next to each other continuously. So we have a block here. Inside the block, you have the first tuple, and maybe you have a second and the third tuple. Maybe someone is going to say, oh, we have a slotted page. Yeah, that's a very different story. Just wanted to simplify the process. Here is to store, focus on what? Whether you're going to store all the attributes in one block or not. Okay, of course we're gonna have a slot array, we have a pointer, etc. That's different, and we have header for the page. We ignore the spot for now. Make sense? So here, if you're looking or try, for example, yeah, let me go over here. First, we're done for this relation, for the next, of the next, and next. Okay, we don't mix, okay? The tuple that belongs to different relation. Good. Now, let's back, we have two queries. The first one, select all the information from the specific user. I will give you username and password, and you retrieve the information from the user. Okay, this one, it looks like I'm talking about the online transaction processing because it's fast, short-running operation, and simple query, and operate on single entity, right? Good. The second one, you want to insert. Let's see, take a look. Assume that we have an index. When you talk about the index like special data structure, we're going to see that. How can you use this one later? Which allow me in order to speed up the access of the data. What does that mean here? If you try to looking for the page, for example, we give me the select this information, where the user give me username and password. If I don't have index, what I need to do here? I need to fetch, in the worst case scenario, all the blocks that associated with this relation to the main memory. Then after that, once I have these blocks in the main memory, I'm going to search them in order to find out which one is going to satisfy this condition. But using the index, I'm going to say, for example, like special data structure, depends whether I'm building my index based on, say, I'm going to build the index based on the user ID, for example. So here we have like user ID, and you have a pointers to the block. If the user ID, for example, 100, go to the block 5, for example. If the user ID 200, go to block 6. Of course, you're going to have a tuple where that, but I'm going to use the blocks just to simplify the process. So you fetch this one first. Based on the value that we have, we're going to say you have to fetch only block 5. If the data exists, when you fetch block 5, so you reduce the number of disks with operation using the index. Make sense? This is my favorite character. You're quiet today. Usually you're quiet. You're still here, guys, right? Thank you. Thank you. Thank you. I was worried because I didn't want to talk. Everything is quiet. So just make sure that we are here. Anyway, so makes sense. This is a simple thing. So back to the workload that we had in the query. So I fetch the index, I fetch the page. So assume that the blocks of the index are available in the main memory. So in this case, we end up, we have one disk without operation, right? In order to find all the data that I'm looking for. Oh, great, because it said select the star. That's good. So the way that layout the data works fine with this kind of query. In other words, works fine. The row store, it works fine with the online transaction processing workload. Let's have another example here. What if we want to insert, let's say, new account, new user? So when you try to insert new user, the same thing here. What? We don't have index, so we don't use index in this case. I can use the page directly to tell me, for example, which block or page has enough space. So the only thing you're going to perform what here? You have one disk without operation, fetch that block to the main memory, insert a new tuple, then write it back, right? So in order to find the page that you're looking for, so we have a two disk without operation. Find the page, so the information gets back. And I can store this old information together in the one unit continuously. All the attributes will be stored together as one unit that belongs for specific all this tuple. Perfect. So the way that organized by data perfect works with the online transaction. Back to this query here. Let's try to find out the number of people per month where we're logging for the government website, and see whether this one works. If I try have kind of query, this kind of query based on what? Based on what is called the online analytical processing. Okay? Because it can be what here? Long-running, complex, and also use large portion of the data. You need all the access user whoever access the system at specific month. Right? Good. When you execute this one, or run this one based on the, let's say, the row base here, okay? So in order to execute this one, the simple thing here, you know that, by the way, the order of execution of the SQL query, all right? The simple thing, we start from the from. Then after that, where? Then after that, you're gonna go to the group by. Then after that, if you have having and the select, distinct, order by, and etc. So the first one, when you try to execute this query here, I need to access here. Access the user account. I fetch the user account here, block by block. Then, once you access this one, you're interested in what? You need to check the hostname. You see that you are going to fetch the whole thing to the main memory, right? Once you fetch this one to the main memory, you're interested, you need to check only one column, one piece of information. So in this case, so far, I need only say, assume that I'm using only 20% of the data that I fetch, right? And 80%, I don't need them. So far, I don't need those information and this information, so far. So you log in this one, you fetch a large amount of, blocks, and you consume only small amount of the data that you just fetch. And the rest is gonna be garbage. I don't need it to pollute, the buffer pool. Okay, then after that, once you can check this one gonna be equal to the government, whatever the host name, you need to check what? You need to extract the information from the last login. So it looks like F for every single tuple that satisfies this condition, right? So in this case, it looks like we have what? 60% of the entire data gonna be wasted through. I don't need this one. For every single block that you fetch, you use 40% for the, this, by the way, is not accurate number, but please assume that we have only 100%, so each of them is going to 20%, it's the column. You see that? We're going to pollute wasting the data. Remember, the buffer pool is going to have a limited space. There's a memory location, they have a limited space. Okay, so if my buffer pool can fit, for example, 5 blocks, this means in this case, I'm going to fetch 5 block or 5 pages, and I'm going to 60% with all the pages that I fetch is going to be useless. Whatever data here, I know that I'm not going to touch it. So I'm going to be polluting the buffer pool. Okay, so in this case, this kind of query, organize or lay out the data on the disk, the store, row store, is bad idea. It doesn't work with the online analytical query. This kind of query requires from what? I need to access only number of columns. I'm interested only in the last login and the host name. If you manage to have your data only that contains last login and the host name, it's going to be great. Make sense? So that's why. So advantage, this N-Ary Storage Model, NSM, or let's say the row store, works fine, okay? Allow me in order to have a fast insert, update, delete. Why? Because you want to insert a new user. Okay, you want to delete user. Easy. All the data gonna fetch one block. I can delete whatever. I manage to have, let's say, best case scenario, one discovered out operation to fetch or find out the block that contains all the information that I'm looking for. Because all the attributes value that be stored continuously in this, that belongs to every single tuple can be what? For a particular tuple can be stored together. Good for the queries that need the entire tuple. Yeah, which in this case, we talk about 2 different workloads. So it's going to be work with the OLTP, Online Transaction Protocol, right? Bad for the scanning large portion of the table or a subset of attributes, especially when you perform scanning large amount of data, portion of the table, and also you're interested only on the portion of the data, not the entire data. And the question that we have a host name and what the host name, what is? I forget this one. Yeah, the last login and the host name. I don't interested for the rest. I'm not interested for the rest of the data. Okay, so this one is gonna pollute the information. So let's take a look to the different type of the storage model. We call this one the decomposition storage model, or the column store, if you are familiar with this one. So in this case, I'm gonna store the data differently here. So I'm going to vertically partition a database into a collection of individual columns that are stored separately. So for every single column that I have, it's going to be stored in one separate page. For example, I do have the relation that contains student ID, name, and GPA. Take the student ID, it's going to store them together on one page. Name, separate page. GPA, third page. Okay? So again, store the value of the single attribute or column for all the tuple continuously in the block of the data. Column-based. So this one is going to be what? We claim that it's going to be ideal for the online analytical parsing. where we're going to read only, mainly we're going to read the large amount of data, and you're just in the portion of the data. I'm trusting, for example, the example that we have, the count the number of people or users, for example, log in per month from specific host name, right? So I'm trusting only 2 columns in this case. So we're going to see how it works. Why is this one better? So assume that the data that we have here, so I'm going to store this one separately, again, for vertically partition data, these columns or database in the collection of columns. That's going to be stored separately. So here, for example, one page, I'm going to just store the host name for all the tuples here. Only one of them. Only one column. Together, of course, you're going to store them continuously in one page. If you need more pages, you can jump to another page, okay? We don't max. Column base, each column going to be stored, all the information that belongs to one column going to store in one place, or one page. For simplicity, assume that we need only one page per column, just to simplify the process, okay? Now let's take a look at the query that we have. Back to this one, we have a problem with that, the way that when you work with the raw storage, right? In the column store, when you perform this query, let's take a look first. You access what? To the user account, okay? And first you need to find the host name is like the government. So I can fetch one block here. You see that? And all the formation is helpful. Someone is gonna say, but not all of them is gonna satisfy the condition that you're gonna like government. Yes, but I'm not gonna lose any information. All of them gonna be part of the selection, the workloads, the if statement that you have in my algorithm, for example. So I need to check this one. Is this one for the host with the values equal government, government? Oh yes. You see that you're gonna scan everything. So in other words, you have zero loose information. Whatever you fetch, you're gonna be part of your processing. That's great. You see that the comparison depends on the query that we have. It depends the way how they lay out the data. It's gonna affect the overall performance. Yeah. If we try to apply this query using the store based of the raw store, sorry. So in this case, we're going to perform too many discompute out operations. And remember, for the first day, we said we don't like to perform too many discompute out operations. We need to minimize the number of discompute operations in order to enhance the overall performance. So the way they lay out the data of the disk is kind of helpful. All right. Another thing we didn't think about it here. Maybe someone thinking about, okay, now I found, for example, this one, the one at the cross, satisfy the condition. Satisfy that the government to say, they equal .gov. Okay, so I need to do what now? I need to find the corresponding match or value for the last login for the host name of this tuple, right? Assume this one tuple number 1, 2, 3, 4, 5, 6. So I need the data from the tuple 1, last login for the tuple 1, and last login from the tuple 3 and 6. All right. So the question here: how can I find the match? If you have a match in one page, how can I find the corresponding match in other page? So it depends on the way how can you organize your data. We do have a two solution in this case. You understand the problem right now, right? I need to achieve the corresponding one here for the first, for the third, and for the sixth. The corresponding value from another page. So I do have one match in one page. I need to find the corresponding match in another page. Because now with the first, the third, and the sixth tuple, only the one that satisfies the condition that govern. So I need to correspondingly check the last login. I need extract the month from the last login from the first and the third and the sixth column, tuple. How can you do that? So we have two ways. How can we organize the data in the, or how can you identify the tuple in the decomposition storage model with the DSM, by the way, or column store. The first one, the fixed length offset. The second one, embedded tuple ID. This is the less common. I'm going to start with this one because it's easy to understand, and then after that show what the most commonly database management use. But this is just an idea. This is not the accurate one, but at least give you an idea what's going on. Let's jump to the embedded tuple ID. So the embedded, simple thing here. So I'm going to do what? For every single attribute in the columns that we have, I'm going to store the tuple ID. it might be the primary ID key, for example. So you see that if we have the data, for example, this is the offset, the original data that we have, A, B, C, D, and we have, for example, for tuple here. Okay, I don't know why this one is not writing here. So in this case, I'm going to do what here? In order to perform this operation here, for every single one, I'm going to say, okay, for attribute this one, A, that the tuple or the page that contains all the information about tuple A, I'm going to do what? I'm going to store, let's say, the ID, let's say the primary key, then after that, the value here. So it looks like you need to have the page and the value here. The page, the primary key and the value that corresponding for A. And here, the primary key and the value corresponding to the first tuple, the second, and etc. It works, but the problem here, we're going to waste a lot of space. So, because in this case, in order to jump, for example, if we find the data that stored here, you need to find the corresponding value. In this case, the tuple, the value of P for the tuple 2. So it's easy to find your way, right? Because you know that 2 here, you need just to find the matching here. Or you can assume that we have a way, how can you jump within each page using the primary key or the offset within this page. This is a bad idea because it's going to consume more space, is not efficient. Okay? In other words, has, let's say, large overhead. Let's take a look at the most common way to do that. The most common way to do that, I'm going to use what is called here the fixed length here. Okay, so the fixed length here, I need to do what here? Let me show you here, go back here. Yeah. In the fixed length, we assume that for all the attributes has the same length. Okay? For example, all the attributes I have, for example, A, B, C, D, or student ID, name, GPA, etc. All of them, the size is going to be what? It's going to have, let's say, fixed length, 32 bits, for example. So if you have a page, okay, and this page can store, for example, 320 bits, for example, just 320 bits, okay? So in this case, you can store 10 value for each page, right? Because all of them is going to have 32 bits. So since we have, for example, each page, for example, can store 10 tuples, you can tell, for example, this is page 1, and you need to, that contains the information about the ID, and the page 2 contains the information about the name, for example, student name. I found match, for example, I need to corresponding value for the first student ID, or the page, or they say tuple 1, and tuple 5. I know what's the tuple 1 and 5 here. Yeah, and I know for sure here the corresponding value here, since every single data or attribute has the same fixed length, so I can use the same offset. I can say jump to the offset 0, bring the information stored there, and use the offset or jump to the offset 5 in order to fetch the other information corresponding to the tuple or let's say column of information for the fifth tuple. Someone gonna say, okay, but what if we have a variable length field? For example, the student name and the ID does not have the same length. Either we're going to have like padding these fields to make sure that all of them have the same length, or maybe use a dictionary here. Yeah? For example, Alice 1, Bob 2. So I have one digit, for example, 16 bits or 32 bits in order to represent every single data that's stored there. That's one thing. So to summarize, this is the offset here. Okay, I mean, if you try to use the fixed length offset, this is the one that most databases use here, and this is using the ID, embedded ID here. For the offset here, for every single page, since assume that we can, this one page, another page, third page, fourth page, each of them can store 5 data, or 4, sorry. Okay, all of them, they have the same fixed. So I can tell, for example, I need the data for the first offset. So I can jump, just retrieve the one, the offset here. Or I need the data here, corresponding to the third. So I can jump to the third. Remember, the goal here is how could you figure out, for example, if you have matched one page, how can you find out the matching in another page? Okay? The decomposition here, I mean, has an advantage. You're going to reduce the number of discompose operation, waste discompose operation, because when you fetch the block, you're going to find all the information that you're looking for are available there. So it's good for the online analytical processing, right? Reading large amount of data, especially if you're interested only in the portion of the attributes. But the problem here, when you tried, for example, in order to, for example, perform point query, or try to insert or delete. For example, I wanted to insert or delete new customer or new users, or update a new account. So in this case, in order to insert a new account, user account, or create a new account with the user or new revision. So the problem of this one, the data are distributed. Student ID in one page, a student name gonna be another page, and etc. Yeah. So in order to insert your data, require from you to perform too much discomfort out operation. In order to stitching the tuple back again. You got this one, right? So it depends what kind of workload that you have, and it's gonna affect you the way that lay out the data. For each single workload, you're gonna have a better way how can we lay out the data on the disk. Okay? So let's give you a quick example, funny one. Assume that we have, let me write this one here. Assume that we have, use a big eraser. So I will give you, like, for example, a small relation that has, let's say, two attributes, and we try to see how can we store the data as a row oriented and the column oriented. Okay. Let me here. Okay. So here, assume we have the relation A, relation R. And the relation R has, let's say, attribute A and B. The attribute has 2 bytes, the size. And the attribute B is going to be only 1 byte. Okay, as the size, okay? Maybe it's integer, maybe it's a char, whatever. So on the table here, A and B, okay? And assume the value is going to be 10, 20, 30. And this is going to be A, B, C. Just a simple example, good? So assume that we're gonna try to store the data as row-based or row-oriented storage. So A and B for every single tuple must be stored together, right? Good. Assume the page that we have can store 6 bytes. A page without the header, etc. We don't care about the header, okay? Just to simplify the process. So in this case, in order to perform the row-oriented, how many tuple can I store here? So let's say the block 1 or the page 1 that contains the following, right? I'm gonna have, for example, attribute A is gonna be 10 and A. Then I can store 20 and B, right? 2 plus 1, 3, 3 plus 3, 6. This is the total number. Then a block 2 gonna contain this information, okay? It's gonna have a 30 and C. All right, this is what they call, the row-oriented or row-based. Good. This have a column. Oriented. So in this case, 6 bytes. Yeah. And 6 bytes, that means you take A, it's gonna store them together, right? So 2 plus 2 plus 2, oh, we are lucky. We can store them, all of them in one block. So block 1 is gonna contain this information. Gonna have in this case what? It's gonna be here 10, 20, 30, the total is 6. And we have a block 2, it's gonna contain the information here, for example, A, B, C, right? So here if we have a select star from R, I need to perform this query. If we have a block, what's right now, maybe there's a not difference, not big deal, because here you can fetch 2 blocks, then you can stitch the data easily here. But here it's much easier for us because the only thing I need to perform here, just need the block here. Let's say where A is equal 10. Oh, if you said A equal 10, you need to select a star. So in this case, if we have index, can tell me just fetch block 1, and the block 1 you're gonna get all the information that you're looking for because you're gonna have the value of A and B because select a star. Here, if you try to apply this query here, here you're gonna fetch this block, you're gonna extract the value of A. Then after that, you need to find the corresponding value match. So you have to fetch the next block in order to fetch the next attribute for the relation R. You see that it depends on the way how to organize the data and how the query that we have here. For example, if I count the number value of A, so here in this case I can fetch only 1 block, and they can perform counting, 3, then done. Yeah, all the information that you're looking for are available. But if you use the row based in this case, I didn't need to have the information that belongs to the attribute P, because it's not gonna help me in this kind of query. Hopefully, guys, that makes sense. The way that's how I organize the data, that's how to organize, storage, and etc. The rest is gonna be much easier right now. By the way, hopefully you get a chance to start working your coding assignment. If you have a problem with your group member, if you are looking for another member, please reach out to the TAs. Don't wait until the last minute. Okay? I add some notes, and hopefully the TA reach you out. I believe you have 3 students. I think hopefully the TA reach out to them in order to figure out maybe they're gonna work together. If you still have a problem, don't wait. Yeah? And act now. Okay. Now, let's take a look at this simple way. How can you do some modification of the tuple? Insertion, deletion, and update. Okay, which definitely gonna help you for the coding assignment 3. Someone is gonna say, okay, why this organized like this? Why you said first you need to perform storage manager, file manager in general? Why you need to fetch you have the data? You need to simulate the process. How can you store the data as blocks? This coding assignment 1 makes sense. In order to try, for example, perform a record manager, you cannot do that, right? Before you find a way, how can you fetch the data back and forth from the disk to the main memory? So that's why we're gonna do the buffer manager first, or buffer pool first, right? Then after that, the third coding assignment, which is the one that covered in this chapter, within this case, do what? You're gonna find the actual implementation for every single attribute. How could you say implement or store, let's say, integer char, etc. So it makes sense to do the buffer pool before doing the record manager. Here you're gonna simulate the process of what? Insertion, deletion, modification of the tuple. You have the tuple, and the tuple is gonna be stored in the block. Yeah, here, this page. And for example, you have number of tuples. You need, for example, to see how can I perform insert a new tuple here, a new page. Simulate this one. Then after that, you need to figure out to see how could you delete tuple from the page. Then the third one, how could you update the tuple of the page? Which is going to be the third coding assignment. Okay, so let's take a look at the instruction. Instruction, we have 3 cases. The simple one, easy case. We didn't care about, we're going to work first with the tuple has a fixed length. Or the tuple has, for example, 100 bytes. This is the size of each tuple. Oh, that's great. Okay. The tuples are not in sequence. In other words, we don't care about the data must be sorted, or the tuple must be inserted in sequence, unsorted order. We don't care. So this is the easy way. So in this case, when you try to insert, that means you can find any place, any bucket or a block that has enough space in order to insert that tuple, right? So the insertion is going to be easy. Either I'm going to be inserting your record at the end of the file, for example, or if you have any deleted slot, any available space, in other words. Okay, so that's easy. A little harder, what if you said, okay, no, wait. The record is not fixed length or variable length. Okay, in this case, maybe it's not easy as the easy case that's in the fixed length. So maybe we need to do what? You need to check here to see whether you have enough space or not. Whether we're gonna do fragmentation or not. Some fragmentation means that you didn't have a space to store the file, hold the data in one block. That means you need to do what? One part of the tuple is gonna be stored somewhere else. Another, let's say, tuple, a block or page. The difficult case, that means the tuple must be in sequence. You need to keep the data sorted. If you want to try to keep the data sorted in order, for example, we have something like this, okay? Assume that we have, let's say, I'm going to assume that the block can store 3 data, okay, 3 tuples. Here we have 1, okay, 4, 5, 6, 7, 8. Okay, this is assume that the ID. So this is the way how to sort the data based on the student ID. Now you want to insert the student ID too. This one must be inserted here. If you want to keep the data sorted, so we have many ways to do that. This is not easy. The way to do that is what? The simple way, you're going to use overflow and store the 2 here. Then later I'm going to reorganize the data once no one works. The second option here you can do here, you can use this, you need to slide everything tuple to the lower level. So what does that mean in this case? So let's say, for example, maybe assume that we have a space here. You slide this one here, you move this one here, you move this one here, you move 4 here in order to free space to the 2. You see that it's not easy. So yeah, notice this one. Sometimes if you want to keep your data sorted and you insert new data to the data, the system is going to spend time in order to make sure the data reflects the change to your database. But if you insert the data or tuple to your database and you don't care about whether the data is sorted or not, okay, so insert this one any place, so it'll be much faster there. Why? Because it depends on the operation that you're going to perform here. Okay? That's what you said, find position and slide following tuples, or maybe you're going to use, for example, overflow, that one way. Then after that, you are going to organize the data. Delete. Delete one interesting thing here. If you try to delete, or perform a deletion here, so this first one, we have a block, and this block, inside this block, we have a tuple, and you need to delete this tuple. Okay? We do have 2 options here. The first one, I'm going to perform what's called immediately reclaim space. What does that mean? I delete this one. When you remove this tuple, now they have a free space. Now I can use it by another tuple. It's going to be free space. That's what they call. It's not easy to do that. Yeah? If we do that, we have a problem. I'll give you an example later. Because maybe there's another tuple that points to this tuple that you just deleted. If you delete now, you need to make sure that you update other tuples. Said whatever you used to point to is gone now. Okay? So the simple one, delete it and immediately reclaim the space. It depends here. When you have a claim space, if you go back, hopefully that one is still there. Oh yeah, great. Assume that now we have overflow. I delete, for example, 5 here. It's removed from here. It's deleted. If we try to immediately reclaim this one, what I'm going to do here, I can move shift 4 to the next block space and move 2 here, then it deletes this overflow. Yeah, that's what they call immediately reclaim the space. And if you have, let's say, by shifting other tuples or moving the overflow. The other thing here is that, okay, mark as deleted, and later we're going to handle this one in the offline. It looks like mark the column or the tuple as deprecated and clean up later. I'm going to organize the data here. So how could you mark this one? This is the way it looks like. You have a table. Sorry, you have a tuple within the page. And this tuple, I'm going to say, this is one, I'm going to add a special mark. Somehow, in order to say, I didn't delete it yet. It's marked as deleted. It's not exist. You cannot use the space now. But later when you organize the data or you can clean it up, make sure that when you clean up, that means if there's another tuple used to point to this place, I need to make sure that update the address at that time. I say this one will be null or whatever. I need to figure out how can you do that. So because this one is not going to be valid, it's not going to exist anymore. Then after that, I can reuse this one. Free the space can be used by someone else. Okay. So here it looks like we need to find a way how to mark that. And also, since we are going to mark many tuples, as you say, as marked deleted, then you need to find a way how can we use the space? How can we get rid of the, organize or clean up my data? Otherwise, you're gonna have many tuples, many space are wasted because I cannot use it right now. Okay, so it looks like you have a trade-off. Immediately reclaim space required in this case, it's gonna be expensive, right? Because you need to make sure that update all the data, move the tuple from one place to another place, and also get rid of the overflow performances. Mark deleted for now, then after that we can clean it up later. It's gonna have a space waste, right? So it's gonna be how expensive the operation immediately claim compared to the wasteful of the space, how much space is gonna be wasted. In order to make sure that we're on the same page, remember I said if you delete one tuple, then we have another tuple is going to point to it that maybe going to cause a problem. I'll give you an example here. Assume that we have a record of tuple y. This is the cylinder, okay? Just to give you like we have 3 tuples actually, or 3 records, x1, x2, and y. In x1 and x2, they're gonna use or point to the address in the let's say record Y. Sorry. So within this one, you have a point to this record. Okay. So what if I'm going to use the physical address? What's the physical address? In this case, I'm gonna say cylinder 15 or whatever, hard disk 1, cylinder 5, track 2, or say platter 5, and block 2, or whatever. Okay? If you delete this one, so that means, and you didn't update the address here, so what's gonna happen here? This guy is gonna be point to what? The non-existent one, right? Because it's gonna be invalid in this case. Or I need to do what in this case? So I need to update all the physical address here. Otherwise, it's gonna be point to non-existent tuple, or block, or record. One way to do that, to handle this situation, we're gonna use like a mapping on the logical address. So that's in the coding assignment 3, you can do something similar. Yeah, so in this case, I'm going to do what? Mapping. I'm not gonna have, let's say, use the physical address here. Maybe you can use, for example, the record ID. In this case, yeah, like logical value. For every single physical address, for example, the record Y exists, a specific disk, etc. Here, I'm gonna use like a logical address. Okay, and here I'm gonna just assign the logical address, use the logical address here instead use the physical address. So all these x1, x2, they're gonna use what? Point to the record Y, but not directly. You're gonna point to what? They have hashing or somehow like you have a mapping table. You can implement this one using whatever algorithm or data structure. The simple thing will have hash table or map in order to figure out how can you search for the address that you have in order here to give me the pointer to the actual record. So here, if you delete the record Y here, so what you need to do here, you have only one space to modify. I don't need to go back to the fetch the record X and Y, X1, X2, then after that update the address and remove the address, maybe have a null value. If you have a null, that means point to non-exist one, okay? But the only simple thing you need to have modify only one place here. So I can leave mark here as deleted, and you're gonna use a null here. That's the one simple thing, all right? So now you delete this one, done, and here you update all the tuple or record is gonna be point. Figure out, for example, if they have a non-value, not exist, that means in this case I know that the record does not exist anymore. Deleted, that's fine. Okay, so in this case I can reuse this space, right? Because now it's going to be used by different space. Yeah, because the physical address here can be used again and they can reclaim the space immediately here, right? The other thing here, yeah, the value here, the logical address is not used by the tuple Y cannot be used until we reorganize the data. So this logical address here, I'm not gonna change it. It's gonna be fixed here, unless I'm not gonna use but in order to represent another, let's say, physical address, right? Mapping to another physical address, right? Because the problem in this case is gonna have a problem, right? Because the other tuple they use this logical address in order to point to what used to be the record Y. Once you organize the data, yes, you can use the logical address. The other thing here, we can handle the deletion using the tombstone. The tombstone is different data structure, simple data structure. The simple thing just to tell me here to handle or mark, okay, old location as a deleted. By the way, what I explained to you a few minutes ago, you know that it's like try to avoid the dangle pointer to existed to non-existing record. Okay. Anyway, the tombstone is like special record, small one can be inserted. Okay, after you delete specific record. Let me show you how it looks like here. You have the same thing here. You have the record Y, and this is the physical address from the side. This is the data how it looks like in the block here. When you delete the record Y here, the simple thing you can do here, I can use like a special amount of data, or special small record. You call this one a tombstone. Okay, is a special record. The system can recognize this one, and in this case, it's going to be only in the beginning of the record. So this is if I'm using, the physical address. If using the mapping, it's easy. Yeah, in the mapping, I'm going to use a none. Yeah, or null value instead of the physical address of that one. Yeah, if you take a look at the tombstone here, I need to give you quick here, go over this one quick here. And the tombstone just speaking within the block here, Let's say I have a relational one. This is the record Y. Okay. I define this one of the first beginning of the Y as a tombstone. This means that this part cannot be used right now. This space cannot be used until we organize the data. When you organize the data, if you have deleted something, you're going to remove it and update all the tuples. I mean, that used to point to this one. And the rest here, yes, you can use. Yeah, this space can be used. Can be used. That's a smart way in order not to waste the space. Okay? Update. Do you have a simple thing here? If the new tuple is shorter than the previous one, great. You know, you have a block here. Yeah? And you need to update this block, this tuple. You fetch this one in the main memory. Now in the main memory. And I update this one, maybe you're going to delete something. So the size of the new tuple is shorter than or smaller than, you say, the size of the tuple before update. So yeah, I can put this in a simple place. Yeah, there is no problem because I know I have enough space. If longer, now maybe we need to figure out more space, whether you have enough space in this tuple or not, or block or not. If not, you need to figure out a way how can you perform this one, especially if you back to the insert. Looks like you're gonna insert a new tuple here. If you want to keep the data sorted, then you need to figure out how can we handle this one. Okay. We don't, of course, we don't use the tombstone here in the updated operation because even if you remove this one, we update this one and sort somewhere else, you just delete this one of this operation. So I believe that's all for today's lecture. Okay. So we talk about the storage manager. Okay. And you figure out the storage manager is connected to the database management system. We looked at different workloads and we looked at the storage model with different way how can lay out the data on the disk, okay, and how related to the workload. If you use online transaction processing, that means it's better to use a roster. If you use data workload, mainly online analytical processing, mainly read a large amount of data, many entities, or large complex query, use especially in this case, you're going to use a portion of the attributes, so go with the column store here. Okay, so this is the reading. It's going to be in the Blackboard. Actually, we have a folder called readings, and you can take a look to the corresponding PDF file for each chapter. The next lecture, we're going to talk about the buffer pool. So what do we need the buffer pool here? So since you have a few minutes, I can go over this one here. So here again, the data we done for this part. Yes, I'm repeating myself over and over. We have the page directory here, and we have here blocks. Okay. Now I need to fetch the page back and forth from the disk to the main memory. How can we handle this one? I'm not going to rely on the operating system. By the way, in the low level, yes, we rely on the operating system in order to perform the lower level, let's say, disk input out operation. Remember we talked about the different type of page, operating system hardware page, operating system page, etc. In the low level, based on whatever secondary storage or storage media that you use, that's the page, we call this one the hardware page. Okay? Or block. Then, when you perform any reading input out operation from the disk to the main memory, the operating system is going to take care take care of the low-level operation. They're going to instruct the operating system. Our operating system is going to say, now we need to issue input out operation. Now we need to perform access to the disk. Now we need to move the mechanical parts of the disk into the right cylinder, etc. Starting reading, transfer the data to the bus. Now we have the data from the it's going to be stored in what is called, the operating system page. Then after that, you're going to have a copy to my database page. Some database management system like Postgres mainly still rely on the operating system, even in the buffer pool. So the data can be mainly stored to rely on the operating system. Also, you have a copy in the operating system page. Most database management system, we're going to see later, you can have a set to specify the commander say, please don't keep a copy in the operating system page because it's going to be duplicate value data. Right? Only keep the copy of the page that you read from the disk only on the buffer pool, or in other words, in the database management system. Buffer pool. Okay. So again, we try to figure out the buffer pool is going to weigh that what. show me how can you bring the data back and forth from the data from the disk in the main memory, and how can, remember, this is going to help us in order to support that the database management system that exceeds the amount of the memory that we have. So it's not like simple operation here. The question again, why don't you rely on the operating system take care of the buffer pool in the top? It looks like virtual memory, because simply the database management system, and now you are in the position you can say that. We know exactly, we looked at the way how the database management system is going to represent the data on the disk. We looked at the way how the database management system is going to represent, to say, the actual value of the attributes and put in the disk. The database management system know exactly what's going on, know exactly what the content, it can interpret it, can understand, can figure out, actually not understand, yeah, you can say understand, the actual content of the data. The operating system, the only thing you know that what you need is now, sequence of bytes, that's what I know. Which one important, which one is not important, I can't tell, yeah? And also in the buffer pool here is not just fetch the data back and forth on the disk. We need to figure out a way that, for example, assume that in the buffer pool allow us only to store 4 blocks, 4 pages in the main memory. We need to have a data structure how to find out my way within the main memory, how to figure out whether the pages exist or not in the main memory, how can I fetch the page from the disk in the main memory if the page does not exist, how can we come up with a replacement policy, for example, if there is no space in the main memory in order to fetch a new page. So how can we handle this one? It's not random. So we have many techniques, many replacement policy, which is going to help us in order to understand exactly and see what the difference between what the database management system and the operating system can do. Okay, guys? So that's all, and hopefully, yeah, see you in person Wednesday. If something bad happened, I hate you. And I hate this semester. So I don't know what's going to happen again. I don't hate you, kind of, because, yeah. Anyway, whatever, ignore what I've said. Okay, see you on Wednesday, guys.